Our first invited speaker, Professor Levi Hargrove from the Shirley Ryan AbilityLab in Chicago and Northwestern University, also in Chicago. And he will tell us about his research. He's been doing research for more than a decade, I believe now. I met Professor Hargrove when I was a PhD student, maybe before, just trying to understand what's going on in the field. So it's been a lot of interesting work over the years done in his group. So please.
So thanks, Max. It's great to be here. Looking forward to sharing some of the work that we're doing. I've titled our talk, Intuitive Control of Bionic Limbs. Whether that's intuitive for us to set them up or intuitive for the people to use, we have more work to do. But I like the talk, like the title anyway. I do have a disclosure. I am a partner in CoApt. It doesn't really have any basis on what I'm going to be talking about this morning, but I am supposed to disclose that I have a financial interest in CoApt. So we're in Chicago, downtown Chicago. We used to be the Rehabilitation Institute of Chicago. A few years ago, we transitioned the building from just across the street to a new modern hospital. It's called, now renamed, the Shirley Ryan AbilityLab. Shirley Ryan was a gracious donor, and the Ryans are the founders of Aon, so a big insurance company. But we moved across the street. In the Center for Bionic Medicine, we have around 63 people in our group. So this was the group that Todd Kuiken founded and I kind of run now. We're on the 11th floor of the Shirley Ryan AbilityLab, and so we have a variety of investigators, students, clinicians, technical staff, engineers, operational staffs, so business support managers, grant writers, etc. So this team really works together, and this is kind of an example of what some of our experiments look like. So there's a lot of people in the room trying to figure out what the patient really is asking for. And so the user is talking to a therapist, because engineers just don't speak the same language, at least not initially. So the therapist is translating what they want the engineer to actually make for a change for the user, so that hopefully this interaction will result in something that is beneficial for this gentleman. So this would be a typical setup. We would have maybe 5 or 6 or even up to 8 or 9 people in the room trying to make configurations that would help a user like this. I'm going to be talking about the leg work today, but we also do a lot of other work as well, some wearable sensing, some upper limb work, a lot of machine learning, control system development, so just a mishmash of things. So we've been working on controlling powered legs since around 2008. We've worked with many of these devices, if not all of them, at some point. And we've published a lot of great work kind of along the way. The one that I'm going to be speaking about mostly today is this open source robotic leg that Elliot Rouse has been the force behind. He was in our group and he moved to Michigan. He has a large lab there. And this is funded by the National Science Foundation. And there are a number of groups that are starting to use this device, so you can get the characteristics of the device online. He has a great web page. A lot of engineering parameters are described, both the knee and the ankle. YouTube videos on how to make and assemble it. So it's a pretty good resource for anyone who wants to get into this activity without having to put in $500,000 in design and develop your own device from scratch. So I wouldn't say that it's not meant for users to use at home. It's meant for research groups to assemble and then do research studies on, for example, a new control system or a rehabilitation intervention, but is not meant to be used for people at home as their daily use prosthesis. And it's not cheap, but it's not expensive. So this would be, you can make your own open source leg for around $28,500 US. So the device is stiff. It's not one of these soft robots, but it has a pretty decent control capabilities, and so this is the Ritz cracker test, and Elliot gave me this video. But you can, even though it's a stiff actuator, you can program the device to behave pretty transparently. And so he's simply using the series elastic actuator, or I think just a torque sensor in this example. And yeah, they have to break the cracker to make sure that everyone believes that it's actually a cracker and not a 3D printed super stiff representation of a cracker. We use it and programmed in an impedance control mode, and this is a mode that a lot of people use when doing this type of work. So you make the device behave like a mass spring damper system, and we usually adjust the parameters associated with stiffness, damping, and equilibrium position. The mass is what it is. You could program a virtual mass if you wanted, but we are usually changing the stiffness, the equilibrium point, and the damping of both the knee and the ankle. And so that leads to a lot of parameters that do need to be hand-tuned by the research team. Has a number of different sensors available on the device. So it has a 6-degree of freedom load cell that is built into it, showing the FZ, the vertical axis force. We have encoders at the knee and the ankle. We have IMUs, and we also incorporate EMG to some extent as well. And I think Helen is going to be talking a lot more about neural control of legs, so I'm not going to be speaking about it in depth. She's kind of developed that field, and I'll let her speak about that this afternoon. But we do use some EMG signals. So we and many others, this is a common way to program powered legs, is to create finite state machines. And so each one of these boxes is a state, and you program the person to go from early stance to mid stance to early swing to terminal swing, and you program those impedance parameters I spoke about before. So you adjust the stiffness, damping, and equilibrium position. So there are 6 parameters to adjust in each one of these boxes. So 3 for the knee and 3 for the ankle. So it seems to be a complicated process to configure these finite state machines. It turns out that we really, after we have tuned these for a number of people, we're really only adjusting about 14 parameters, even though there's around 200 or so that you could adjust. It turns out there's around 14 that we do adjust commonly, and we try to make those related to things like how much energy do you need to lift up the stairs and things like that. So again, that's why the therapist is talking to the engineer in that early video, so that we can convey that information of what needs to be changed. I'm going to come back to the state machine because recently we've been removing it entirely, and we have a new way to control. But this we've done work on this since 2009 to develop this state machine. We also do intent recognition, so we try to predict what the person is trying to do every step. So every time the foot comes off the ground and every time it makes contact with the ground, we try to predict what the user wants the device to do. So they want to take a level ground walking step. Do they want to go up and down stairs? Do they want to walk over slopes? Do they want to walk slow and fast? So we estimate each time, and we know when the foot comes off the ground from the load cell sensor, and when it makes contact with the ground from the load cell sensor. So we have a very short period of time that we can estimate what the user is trying to do, and we use machine learning to do that. So this gentleman actually had TMR on the leg as well, and where you kind of use all of those sensors and have tuned a real-time control system, and this is what a person can do. So they don't think about controlling their knee or ankle independently. They think about walking or ambulating, and these are all the different activities that could be restored. These are the EMG signals that are kind of generated as the person's walking. And then we can do kind of non-weight bearing independent control where you just use your EMG signals to control the knee and the ankle. So this video was taken in 2012, and kind of since that time, we've tried a few different legs, but we've mostly been trying to make it work like this every time without having a team of 8 or 9 people set up the device for the user. So that's not glamorous work, but it's hard, and someone needs to do it. So put it on and go. And honestly, the EMG aspect has been very challenging because just getting EMG signals inside of a socket for the leg is very difficult. So That's why we're over here, and we want to try this out with some individuals who have maybe had osseointegration and they don't have the socket to deal with, so we're excited to see what that capability might have, might provide for us. We do know that EMG, this is mechanical sensors plus EMG plus some information about gait, and these are classification error rates, so lower is better. And we do know that if you incorporate that type of information, that the system behaves better. We just haven't been able to make use of it in a practical way. And so these are kind of offline experiments, and these are online experiments, but we know it has potential. It doesn't always work, right? And so sometimes people don't notice a misclassification, right? So the control system made a mistake here, but the impedance parameters are so similar between walking and walking up a slope, the person doesn't even realize it. More often, the person feels a perturbation, but it's not necessarily dangerous. It kind of feels like I stubbed my toe, or it feels like I'm walking in a hole. And then, you know, these perturbations become more and more substantial, more and more dangerous as the video goes on. But this one, it's too stiff because it was a misclassification to walking, and it didn't safely lower them down the ramp. So they kind of stiffened up, and the person kind of jackknifed over the device. This one didn't transition to walking at the bottom, so it kind of felt like he was walking in a hole. This is a dangerous one. You'll see what happens. Made a mistake going down the stairs. It led to a mistake where the prosthesis study wanted to go up the stairs, right? So this just highlights kind of the challenges associated with this work. Fortunately, we have been able to correct that particular type of mistake so that it doesn't, I don't think we've had one in several years, but they all need to be attended to. Otherwise, it's bad things can happen. So again, that's like 8 years of work to make sure, just to iron out these few possible mistakes. And we do other stuff in the 8 years, but this is a big portion of it. When it behaves well, this is with the open source leg, kind of a newer video. This is a produced video. But you can see, again, a user using the device to walk around on a number of different activities. This is in our new building and in our new lab. And we are able to get kind of outside of our room, our experiment room, around the hospital and around the community in Chicago, but always under the supervision of a research team with this particular device. But again, we can program it now. We have pretty smooth ambulation up and down slopes. We can do sit to stands pretty reliably. And again, this gentleman is around 75 years old, but he is a very good walker. I wouldn't say that this device is enhancing his function, but you know, he's definitely helping us develop the control system. So you can control two legs at the same time if you want, right? So this is we were using an able-bodied adapter, and we're trying to control both of these legs at the same time. And so the legs are talking to each other, and they also have the capability to communicate to the user through their EMG patterns as well. In this case, we just are using mechanical sensors, but we do have the EMG capability in. We have to modify our state machine to take advantage that we're using two legs at the same time. And again, starting to replicate reciprocal stair climbing for a bilateral lower limb amputee is very difficult. Tommaso Lenzi just published a video of an amputee doing this with powered legs. It's very impressive. Actually going down the stairs is harder than coming up the stairs, and we haven't figured that out yet, so you'll see the video stops right at the top of the stairs, right? But work in progress, we'll get there. And then, of course, able-bodied adapters are one thing, and high-functioning individuals are one thing, but this is a real user who has a bilateral amputation. He's heavy, he has his contractures, and he's just taken his first few steps with these powered legs. And so someone like this is who a powered leg could potentially help with much more research and development needed to go in and make it safe. And so walking up slopes and walking upstairs is glamorous, but what this guy really needs is this. He just needs to be able to stand up out of his wheelchair. And so, you know, we're still have therapists and people helping out there, but seeing him try to stand up with two genium legs, he just can't do it at all. So This is an example of where we're using the power in a sit-to-stand circumstance just to stand him up. Even if we made the legs behave more or less passively after he stood up, that would be functional benefit for this user. So this is kind of where, you know, we show the videos of people doing all of these different activities. These are where it's going to make the impact the soonest, I suspect. So again, I kind of have a bit of a love-hate relationship with state machines. So we didn't start out trying to develop state machines to restore ambulation of all these activities. We wanted to do machine learning to predict how the person wanted to ambulate. And we designed these state machines just as an enabling tool that allowed people to walk. So what we've been doing more and more recently is we've just been learning the motor currents from the sensor data directly. So we have 50 or 60 people that have walked on these powered legs. We have input sensors. We have output motor currents that are being used. And so we can just get rid of the state machine and use deep networks to learn the mapping of the input sensors to the output controllers. And so that's kind of what we're working on at the moment. And it actually works. It was mind-blowing that we're able to have this person, and the network wasn't trained on this person. He'd never seen it. He had walked with the powered leg before. But we're able to start replicating walking. So this is no tuning parameters. You just have a pre-trained network of many different users, and the network can generalize to the person's height and weight and amputated side. And you can do activities like stair climbing as well. And so there is a bit of a catch-22 in that you needed to have those sensors from other users. So essentially the deep network had learned what the state machine structure was. And so what we're doing now is we're imposing models through OpenSim to see if we can learn these mappings from musculoskeletal models rather than real data. I think that'll be harder, but in the end it might be a more powerful tool because you can customize, you can provide potentially customizations of the model rather than relying on this data generated approach. And if it works well, you can probably put in new activities that haven't been configured, but we'll see. So that's ongoing work in progress. So with that, I'll conclude. Looking forward to the rest of the meeting and collecting some data here next week. It's going to be a lot of fun. And then thanks for having me.
There's one question, and one of the participants online wonders, are you planning or are you working with exoskeletons already?
We are working with exoskeletons, yes. We're just kind of starting to work with exoskeletons. So Jose Pons is the scientific chair of the Legs and Walking lab at the Shirley Ryan AbilityLab, and he has some exoskeletons that he's working with. And so we're starting to migrate some of these approaches towards exoskeletons. So we're very preliminary, but it's on our development path. So I would say we're just dipping our toes in the water. Yeah.
And one more question. Does the control strategy need to change as a user learns to use them?
It probably should change. However, we're not there yet. So basically, you know, that's when the question is it intuitive or not? So the person has to learn the control strategy to some extent, right? So it is what it is. It allows for variable speed walking. It'll turn. You can go up and down stairs. You can go up and down with either foot. But the person still needs to walk with this heavy powered leg. And so they still have, they still have gait asymmetries, things like that. So we'll have to get more experience and walk with it longer before we can figure out if there's a way that we can adapt it as the person walks. We have ideas, but we haven't tested it enough to say that it's beneficial yet. Hopefully we'll get there. Thank you.